Swayam Prabha. Digital India. Educated India.
Hello and welcome to this manufacturing process technology part 1 module 16. We are going to talk about furnaces today and also a little bit of design for the different castings. So furnaces used for melting metals, they kind of differ widely from one another. There may be for example, an induction furnace, there may be a cupola furnace, there also may be a side blow converter. So depending on the heat transfer modes or depending on how you basically apply energy so that you can melt the material, you can categorize these into various different types. The selection of a furnace really depends on mainly the metal chemistry which is being used, and also the maximum temperature that is needed. Now, in some cases you need to superheat the material before pouring into the mold, so that it can reach longer distances and fill up, let us say, serially placed molds in a gated pattern or something like that. So in that event, the overall temperature has to be much above the freezing temperature of the material, and that is called superheat. So not all furnaces can superheat or boil the material off, because there is some kind of a rate of heating limitation and also the maximum temperature limitation of these furnaces. So the other important factor in making a selection are the size and shape of the available raw materials, and the metal chemistry also decides not only the control of standard elements, but also some important mechanical properties like machinability. So therefore, some furnaces may be more prone to hydrogen attack or nitrogen attack, and they may not be selected because the material chemistry there which takes place because of hydrocarbons, oil, dampness in the furnace gases, etc., may not be amenable to develop good machinability of the material. So there is a very important term called fluidity of the material when we talk about melting the material, and is basically the optimum temperature after melting which decides what is the overall fluidity level, and fluidity is a requirement basically. So the fluidity can be referred to as the relative ability of the liquid metal to fill in the mold at a given temperature, and normally if the viscosity of the fluid metal is lower, then the fluidity is higher, and vice versa. So if it is thick metal slurry which is, or thick metal which is moving, thick metal liquid, or if it is a thinner metal liquid which the viscosity falls down because of temperature, so the thinner would move faster obviously. So there are many ways to measure this solubility, this fluidity. One of the typical ways is to use a spiral channel and see at, with a gravity feed how much distance of the spiral can be covered by this metal before getting solidified, and that can be a good idea of what is the fluidity of the pouring material or a pouring metal. So obviously you need a case where you have sufficiently high fluidity so that the overall reach from the pouring basin to the runner all to the gate of the metal cavity or cavities, for example, in gated patterns as I showed you before, that has to be attained. Okay. So the fluidity always is checked before doing a casting or pouring into a casting, so that you can see whether the input material, the output material that you are having out of the furnace is of the correct fluidity or correct level of requirements imposed by the molds. So if we examine the temperature fluidity curves for various metals, we find that the higher the fluidity of a metal, the lower the difference needed between the pouring temperature and the melting temperature. Okay. So obviously if the viscosity of the metal at liquid state is lower, then you will need this difference between pouring and melting temperature to be more or less minimal value, because obviously as soon as it is going to come into the melt, it is going to be flowable, the viscosity is going, and you need not add any superheat to make the viscosity change with temperature. For completely filling up the intricate thin sections of the mold, this difference should be a minimum, so that it can go everywhere in the mold. And some of the furnaces are shown here which can do this job. For example, induction furnace can add heat up to 1750 degrees Celsius. The basic principle here is a induction coil. It is a copper induction coil where there is a magnetic field which is generated because of a flow of current within this coil, and this magnetic field induces small local currents within the material here, and these currents are also known as eddy currents. So, these eddy currents would be able to melt the material completely by adding I square R T intense heating, and this is by a non-contact mode. So, you do not have any problems of temperature gradient from the wall to the center of the furnace, as you can see here. So, you are heating through induction and you are heating the central core of the material until it hits the melting point, and you can go to a temperature as high as about 1750 degrees Celsius. So, typically the metal is kept in a crucible. So, the crucible can sustain the high temperature conditions where the metal gets into liquid state. There is a refractory cement which holds this crucible in place, so that the cement is able to sort of expand and hold the strength at a higher temperature. So, whatever outflow of heat happens from the molten metal to the furnace can be sort of protected on one hand, and another the strength can be kept intact, so that this cup does not vary in size or shape, or it does not go down. So, that is how the induction furnace is. Obviously, there is a side blow converter which can heat up the metal up to 1700 degrees Celsius. So, here the metal is in the lower pocket of. So, the metal here is in the lower pocket right about here, as you can see, and this air theories is basically pumping in the hot air into the system, so that there is a heat transfer between this blow by and the metal which is there, and the gases kind of escape from the top side of the furnace. So, these side blow converters can be heated up to about 1700 degrees Celsius. There is this famous cupola furnace which can go up to slightly lower, about 1650 degrees Celsius or so temperature, which has a, you can see this is the orientation of a cupola furnace. So, this right here is the melting zone, for example, and again the theories are able to send hot air throughout this melt, where there is slightly impure form of iron also which can be loaded and slag can be extracted. So, you have a charging door through which the main charge flows into the cupola furnace, and there is actually a slagging spout here which can help you to clean the metal slag. So, that is how furnaces are kind of designed, and let us now look at the main important issue of how to design a particular casting. Okay, when we talk about filling times or solidification after the full cavity has been filled with metal, etc. So, let us first go discuss the gating design in a pouring process in great details. So, what is gating? So, you know that after the metal is melt and poured and injected into a mold cavity, gating design kind of ensures the distribution of the metal in the mold cavity at a proper rate without excessive temperature loss, turbulence, and entrapping gases and slags. So, obviously, one thing that really comes into picture here is that the liquid metal being very heavy is poured very carefully and very slowly, because it should not be able to damage by its own weight the sand mold which has been made, and which otherwise is not a very high strength system. Okay, so, it is poured very slowly. So, as I was just discussing, the liquid metal, if it is poured very slowly, because fast metal flow may lead to the damage of the mold, the time overall which the metal would take to fill up the mold would be very high. Okay. And so, solidification may start happening even before the liquid metal reaches the mold cavity. So, there has to be a proper design, and this is actually a pressure driven flow, because there is going to be a pouring basin at some potential energy, and the metal is going to be in liquid state. So, it comes down like a from an overhead tank, and it fills up the casting space, the molding the mold cavity, and for filling it up it is through a channel that it fills up. So, it is essentially a piping based network which would allow the liquid metal to go into the mold cavity. So, there are many issues here. One is obviously the gas solubility, because if supposing I heat or superheat the material too much, then there may be a problem of gas solubility, because it may cause a overall faulty metal structure. So, even that is also not allowed. On the other hand, if the liquid metal is poured slowly, the time taken to fill up the mold can be rather long and solidification may start. And somehow we have to develop an intermediate solution, so that the liquid does not impinge the cast, and at the same time it has enough time for it to flow into the material, and it does not also damage the material structure as such by having minimum gas solubility. So, for doing that, let us investigate what kind of gating designs are normally available. So, normally there are 3 different kind of gating designs. One is a vertical gating system, as you can see right here. So, this is the pouring basin, and this part is the, you can say it is a sprue, or it can be some kind of a down draft of the material, and it directly enters into the mold cavity, which is at the bottom here at a different height. Okay. This is a simple vertical gating system. Similarly, you have a bottom gating option, where you have the mold being filled upside down from the bottom to the top. Okay. And so, on the other side, you can always open a riser here to see if the material comes and fills the whole cavity or not. And there is atmospheric pressure on one side, which actually gives this liquid metal in the pouring basin to flow in a downwardly manner and go into this region, which is actually known as the runner region. Okay. And this right here is the gate region. So, these are the 2 different kind of gating systems. You obviously can have horizontal gating as well, when you can actually not bother about using gravity, but actually do pressure die casting by introducing metal at a certain pressure, liquid metal at a certain pressure. So, it can become a high yield process. Okay. So, let us now talk about some aspects related to how we can do this gating design. So, in the simple vertical gating design, supposing we are talking about the point 1 and the point 3. Okay. So, if I want to use the energy balance equation between the point 1 and 3 in this particular case, I can have the point 1 at an atmospheric pressure. So, let us write P atmosphere here divided by rho g. So, that is the pressure head, this is the density of the liquid material, this is acceleration due to gravity, plus the velocity head at point 1, which is assumed to be 0, because the velocity is assumed at the top of this particular horizontal simple vertical gating design to be 0. So, the velocity head is 0, plus the potential head, which is actually the height h t over and above the mold surface, as you can see right here, this is h t. Okay. And this becomes equal to the the pressure which is there at the point 3 of the material. Okay. So, basically the mold we are assuming is open to the atmospheric pressure. So, obviously the pressure at 3 also at the end of this sprue would also be atmospheric pressure. So, let us say P atmosphere here divided by rho g plus the velocity at point 3, and I assume this velocity to be V 3 of the liquid metal. So, obviously the velocity head would come out to be V square by V 3 square by 2 g, and then you have the potential head in this particular case, which is actually equal to 0, because if I assume this to be the datum line, this to be the datum line. So, we are at the bottom. So, we assume this to be 0 here. Okay. And so, that is how you can actually envision this equation. So, this gets cancelled off and you are left with V 3 equals root of twice g h t. So, that is the velocity at the end of the sprue right here in the piping design that you are looking at here for doing the simple gating system. So, let us now calculate the time, assuming the velocity at 3 is V 3, let us calculate time of filling of this mold So, obviously, if the mold volume that we are considering is V here and Tf is the time of filling. So, the Tf would become equal to V divided by the gate area times of the velocity. So, if I assume the gate area to be equal to a g, which is the area right about here. Let me just rub all this off to tell you about exactly which region is the gate. So, this right here is the gate region through which the material is entering into the mold cavity, and so this area here is a g, cross sectional area is a g. So, supposing there is a diameter of this particular tube. So, a g should be equal to pi d square by 4. Okay. So, velocity is V 3, gate area is obviously a g. So, the amount of time which is needed to fill is the total volume of the mold V divided by the volume flow rate of the liquid metal through the gate. Okay. So, volume flow rate of the liquid metal through the gate region, and here the volume flow rate of the liquid metal through the gate region is a g times of V 3. Okay. So, the area of cross section times of velocity, which is the distance per unit time. So, that is an idea of how you are calculating the Tf. So, therefore, the total time of filling is the total volume of the mold times of the gate area times of the gate velocity V 3. So, that is how you can calculate Tf and you have to now try to balance that Tf should be at least equal to a time where solidification just does not happen or does not start to happen. So, it is kind of quite simple in a way, and this is a simplistic expression, although in real sense there will be many more factors like friction and velocity reduction because of friction, etc., particularly in the gated patterns of long kind that was illustrated in the earlier modules. So, having said that, I think we will go to the next design, which is actually the bottom gating system, and look into how different this gating system is going to be. But in the interest of time, I am going to close this module. This analysis will be carried on in the next module. Thank you.